I welcome once again in this new lesson. So in this lesson we'll see the relationship between electric current and drift velocity, and then we'll derive Ohm's law. So before starting the lesson, let me define the parameters. We have a conductor of length L, area of cross section A, connected to a battery of potential difference V. The current I in the circuit is I. Once we switch on the circuit, electric field develops inside the conductor. So the value of the electric field is given by V divided by L. Because of the electric field, these electrons, they tend to drift along this direction, and the value of the drift velocity is given by E by m into tau, as we saw earlier. So one important thing to remember here, so this is only the value of the drift velocity. In vector form, we take into account both the value and the direction. So here we are using only value. In vector form, if we use this for positive charge carrier, then we have to use plus E. In vector form, if we use this for a negative charge carrier, in that case we have to take minus E. N is the density of the electron, E is the charge of the electron, T is the time taken by the electrons which enter the conductor at the right end to pass through the conductor to the left end. That is, T is the time taken by the electrons to travel from this end of the conductor to that end of the conductor. Obviously, time is equals to distance divided by drift velocity. So therefore, T is equals to L divided by Vd. Now Q is the total charge contained inside the conductor. So we can calculate total charge using this formula. Total charge equals to density of the electron into volume of the conductor into charge of the electron. So therefore, Q is equals to NALE. Now after this, we'll derive expression for the current passing through the conductor. Now since we know that current is equals to charge divided by time, so this was the time taken by the electrons to travel from this end to that end. So during that time, the current in the conductor, I is equals to Q by T. So if I use the value of Q and T here, so we will get this expression. So this is the relationship between current and drift velocity for a given conductor. Now we have a new term here called current density. So current density is current per unit cross-sectional area, or I divided by A. So the symbol for current density is J. So J is equals to this expression, and hence AA gets cancelled. So this is the expression for J. Now this J is in scalar form and this J is in vector form. In vector form, we take into account both the direction and the value. So if we use this for the positive charge carrier, in that case we have to use plus E, and if we use this for the negative charge carrier for electrons, in that case we have to use minus E. So this is for the positive charge and this is for the negative charge. After this, we'll derive Ohm's law. When the potential difference V is applied across the conductor, the drift velocity in terms of the potential difference is given by this expression. Again, this is the value of the drift velocity as we saw earlier. Now we can replace E by V divided by L. Then Vd has this expression. Now if I use this expression of drift velocity in this formula of current, then we will get this expression. So further simplifying this expression, we'll arrive at this expression. So V divided by I is equals to m into L divided by NE square tau into A. Now at constant temperature, the mass of the charge carrier, the length of the conductor, charge density, charge, relaxation time, and area, all these terms are constant at constant temperature. So therefore V divided by I is constant, so which is nothing but Ohm's law. Therefore V divided by I is a constant. So we call this constant as the resistance of the conductor. So if we compare this to expression, then R equals to this term, mLNE square tau A. Okay, so this is the new expression for the resistance of the conductor in terms of these parameters. Now we have another formula for resistance. So R is equals to rho L by A, where again L is the length of the conductor, A area of cross section, and this term is called resistivity of the conductor. So this resistivity is nothing but resistance per unit length per unit area of cross section. So if we compare these two formula, so we also have L and A here. So resistivity in terms of the mass of the charge carrier, the density of the charge carrier, charge and relaxation time is given by this expression. The reciprocal of resistivity is conductivity. So conductivity is 1 divided by rho. So 1 divided by rho is this expression, which is given here. Now relation between current density and electric field. So we have written here expression for drift velocity. So this is in a scalar form and this is in vector form. So by using this vector form, we can find both the value part and the direction part. And also we can use this expression for both the positive charge carriers and the negative charge carriers. Now, since in conductors, the charge carriers are electrons. So if we use this expression of Vd in vector form for electrons, in that case, we have to use minus E here. So this is the expression for drift velocity of electrons. Drift velocity of electrons for a conductor. So now J, now this J, the current density, we saw the expression in the previous page also. So if we use the value of Vd from here in this equation, then we will arrive here. So therefore J is equals to Ne squared tau divided by M into E. Now this term, we can replace this term by the conductivity of the conductor. So therefore G is equals to sigma E. So this is the vector relationship between J and E, and also we can use it for the positive charge carrier as well as negative charge carrier.